Welcome to Spring LIB.
For this problem, we have been given 8 recursive relationships with initial conditions for different sequences. Now, the recursion method is a really nice, compact way to put down sequences. Unfortunately, to find like the 100th sequence or the 100th term in the sequence requires us to know all of the other previous 99. So sometimes it's nice to be able to write these sequences without having to use the recursive elements. So we're going to take recursive definitions of sequences and change them so that they are not recursive. So let's take a look at the first one and see how this works. We have a to the n equals 3 times a to the n minus 1. Okay, so that's our recursive definition. And we're also told that a sub 0 equals 2. So what we're going to do for this problem and all of the subsequent ones in this example, we're going to find maybe the first, maybe up through a sub 4, and see if we can find a pattern that emerges, okay, that we could use to define this sequence. So a sub 1 means I take 3 times my prior one. So that'll be 3 times 2. How about a sub 2? Well, that's going to be 3 times the prior term, 3 times 2. Well, a sub 3 will be 3 times the prior term, which is 3 times 3 times 2. Okay, and you can hopefully see the pattern emerging here. In each case, I have 3 to the same power as that, as the base. A sub 4 has 3 to the 4th. A sub 3 has 3 to the 3rd. So we can take this sequence and say the nth term of my sequence will be 3 raised to that nth power times 2. So while the recursive definition is nice, our new definition, we can find the 1000th term and only the 1000th term and not have to find all of the ones leading up to it. So it is convenient to be able to rewrite these. Okay, B. Our recursive definition says a sub n equals a sub n minus 1 plus 2. And we're going to start a sub 0 equals 3. Well, again, let's do the first few here and see if we can see a pattern emerge. Okay, so a sub 1, we take the prior term plus 2. A sub 2, we take the prior term plus 2. A sub 3, we take the prior term plus 2. Sometimes it's useful to actually do the math here, to do the addition or the multiplication. If possible, I'm going to leave it out, spread out like this, because then it's, rather than just seeing 3 and 5 and 7 and 9, this really shows how the numbers are getting put together. And I think it makes it a little easier to see the pattern. Okay, let's just do one more. That's the prior term plus 2. So in this case, if I look at what the pattern is, in each case, I have a 3 in the beginning, so 3 plus. And then I'm adding 2, and I'm adding 1 more 2 each term. So I'm adding 2 times n. So for the a sub 3, I've got 3 2s. For a sub 4, I have 4 2s. So here is my definition for this sequence. Okay, next. I have a sub n equals a sub n minus 1 plus n. And in this case, we are starting with a sub 0 equals 1. So let's put out a few terms here. Okay, a sub 1, I take the prior term plus n. Okay, a sub 2, I take the prior term plus n. Prior term plus n, prior term plus n. Okay, so what pattern do we see emerging here? Well, in each case, it's pyramiding. So I have this plus 1 just in the front here. So I think whatever I do, I'm going to say 1 plus. And then I've got a pyramid. I've got a sub 1 is 1. A sub 2 is 1 plus 2. A sub 3, 1, 2, 3, 1, 2, 3, 4. Well, we do have a formula for adding the first n integers. It is n times n plus 1 divided by 2. Okay? And if you recall why this works, I'll take a sub 4 as my example. I have, if I add the first and the last, I have, that's n and then plus 1, so that's 4 and 1 is 5. And every pairing is going to equal that same amount, and I'm going to have n over 2 of those pairs. So n plus 1 times n over 2 pairs. So this is my sequence, or the definition for this sequence, not using a recursive definition. Okay, on to D. D says a sub n equals a sub n minus 1 plus 2n plus 3. And I'm going to start with a sub 0 equaling 4. A sub 2, a sub 3, a sub 4. Okay, so let's see what we get. First, a sub 1, we take the prior term, plus 2 times 1, plus 3. Okay, a sub 2, we take the prior term, plus 2 times n, plus 3. A sub 3, prior term, plus, well, that 2 times 2, let's just kind of put that together here, plus 2 times 3, plus 3. Let's just do one more. Unfortunately, I'm not really seeing a solid pattern come out. There's the prior term, plus 2 times n, plus 3. Lots of 4s and 2s and 3s, but nothing really is jumping out at me. So let's try another tack. Let's actually add them up and see what we get. Okay, and I'm just going to change a different color here. So I've got 4 for the first one. Next, I have 9. Then I have 16. Okay, now I see a pattern. By adding these, I can see that I'm going up. These are all perfect squares. And I'll just put this one in blue as well so you can really see that pattern. Now, this is not n squared, though. When n is 0, it's 2 squared. When n is 1, it's 3 squared. So it looks like I'm taking 2 plus n, and that's what I'm squaring. So when when n is 4, it's n plus 2, or 6 squared. When n is 3, it's 2 more than that, or 5 squared. So there's that one. So sometimes it's easier to see it when you write it all out. Sometimes adding it shows the pattern best. Okay, let's do E. A sub n equals 2 times a sub n minus 1 minus 1. Okay, and we're going to start with a sub 0 equaling 1. Okay, so let's begin. A sub 1. I take 2 times the prior one minus 1. Well, that equals 1. That's exactly where I just started. A sub 2, I'll take 2 times the prior one minus 1 equals 1. I'm not going anywhere. A sub 3, 2 times the prior one minus 1. This is not changing. So for in this case, my sequence is 1. Every single term is going to be 1. It doesn't matter which n I'm at. So let's look at F. F says a sub n equals 3 times a sub n minus 1 plus 1. And I'm going to start with a sub 0 equaling 1. So let's do a few here. Take 3 times the prior, 3 times 1, plus 1. A sub 2, 3 times the prior, plus 1. Well, okay, let's just do one more of these. Take 3 times the prior, plus 1. Well, let's take a look at this one here. I want to get rid of these parentheses. This gives me 3 squared plus 3 plus 1. When I go to a sub 3 and I multiply by 3 again, now I have 3 cubed plus 3 squared plus 3 plus 1. What about a sub 4? If I multiply that by 3, I get 3 to the 4th plus 3 to the 3rd plus 3 squared plus 3, and then I do plus 1. So my pattern here, these are all descending powers of 3. 3 to the n plus 3 to the n minus 1 plus 3 to the n minus 2, all the way down to 3 to the 0. So how do we write this as an actual definition? I can see the pattern, but what do we write? Well, I'm going to show you the solution, but we're also going to talk about how we get to it, because there is a way, a formula to write this. Just like there was a formula to write the sum of the first n integers, there is a formula to write the sum of the first n powers of some given base. Okay, so I'm just going to write the formula first, but then we're going to talk about how you can actually find it if you didn't know this. Okay, so what it is you take the base to the n plus 1 power minus 1 over 2. So this is the actual sequence for this. But how did you come about something like that? That's not one we use a whole lot. So I'm going to put this in blue just so it stands out. And I'm going to write down what we saw here. So a to the n, and I'm just going to use a generic p to show that it doesn't have to just be base 3. It can be any base. So I'm going to just use base p. So I have p to the n plus p to the n minus 1 plus p to the n minus 2 all the way down to 1, or p to the 0. Okay, actually, I'm just going to write this as 1. Now, let's take this, and I'm going to multiply both sides by p. So that gives me p to the n plus 1, p to the n minus 1, all the way down to p. Okay, so I just multiplied every term, both sides by p. Okay, well, let's take a look at that right-hand side. This is a sub n. All I need to do to make it a sub n is to add a plus 1. And as long as I add then a minus 1, I haven't changed that side. So what I have over here is I have p to the n plus, I'm sorry, not p to the n. My apologies. I said the right thing, I wrote the wrong thing. It's a to the n, because this whole piece here is a sub n. This whole thing is a sub n. I'm going to get my subscripts and superscripts mixed up here. Okay, because this, when I added that plus 1, that's a sub n, subtracted 1, so I haven't changed anything. So I have p to the n plus 1 minus 1. Okay, sorry about getting that subscript and superscript mixed up. Hopefully this is making sense. Now I want to solve for a sub n. So I'm going to subtract a sub n from both sides. So on the left-hand side, I have p minus 1 times a sub n if I factor that a sub n out. On the right-hand side, I have p to the n plus 1 minus 1. And now I'm going to divide. So I have come over here, a sub n equals p to the n plus 1 minus 1 over p minus 1. So that is for any p, any base, that's my answer. So in this case, p is 3. So that, in other words, I have 3 to the n plus 1 minus 1 on top, and the bottom is going to be 3 minus 1, or 2. So hopefully that helps. You might have known this one already. If not, hopefully this will help if you see it in the future. Okay, we have 2 more to go. Let's look at G. G is a sub n equals n times a sub n minus 1. And we're starting with a sub 0 equals 5. Go down and look at a few entries here and just give myself a little more room. Okay, so a sub 0 is 5. A sub 1 is n, in this case 1, times my prior term. A sub 2 is n times my prior term. 3 times my prior term. 4 times my prior term. Okay, well this right here looks a whole lot like a factorial. The only difference is I'm multiplying it by 5. So a sub n is going to be 5 times n factorial. Okay. And last sequence, H. A sub n equals 2n times a sub n minus 1, where a sub 0 equals 1. Okay, so Same process. We're going to see if we can find a pattern. A sub 1, it is 2 times n times my prior term. Okay. And all those ones in there, I'm just going to simplify that to 2. A sub 2 is 2 times n times my prior. Okay. A sub 3, 2 times n times my prior. A sub 4, 2 times n times my prior. 2, 3, 2, 2, 2. Okay. Make sure you can read that. So let's see what we have here. We have a lot of 2's going on. We also, every time we're multiplying by the next integer up. So this is looking very much like a factorial. 4 times 3 times 2, 3 times 2, 2. Okay, so those are actually, let me keep it in the same general spot. Okay, so it looks like in each of these, I have a factorial going on. But what else do I have? So I've underlined the factorial piece. Okay, here I have a 2, 2 2's, 3 2's, 4 2's. So it looks like I also have 2 to the n going on because every one of these terms, I've got one more factor of 2 plus the factorial piece. So there is the definition of this sequence as well.